actually a video. Yep.
All right, math club today, Loyola 8 at 4. I'm teaching how to do 2 really amazing math card tricks.
Card tricks.
Mm-hmm. One of which uses things we've talked about in here. You never know it. Yeah, so 2 card tricks, 4 p.m., free food, I guess. So the legend goes. What would you like to talk about? Whoa, thank you. Yes. I know just what to say, Sydney.
I figured after you
Yeah.
making sure we all did something on it.
Indeedly do. Indeedly do. Let's see. I don't know why I'm dead Flanders notes. Okay. Before we do that, let me pop at least one thing on the board. We're probably going to have time to work on, finish this up today in class. I'm going to give you a little time to, is anybody done with the homework? Awesome. Then you're going to get time to work on it today. I like that rhythm. We've kind of been doing that a little bit. I want to make it more so. So, since you'll probably be pretty good with it, for Wednesday, if you just wouldn't mind, reading Theorem 4.2. This starts on page 81. And so, read the theorem and the proof. That would be awesome. It may or may not make sense. We'll go through it, and then it'll hopefully be really clear to everyone. And then as far as you can in chapter 4, as far as you can stomach, as far as possible, as far as you want, just get Theorem 4.2 for sure. That would be absolutely splendid. All right, Sydney. And these are chapter 3, I can't even remember. Are these 3 or 4?
Part 3.
3, thank you. And what would you like to talk about?
Can we start with number 22?
Oh, I like the sound of this. Start indicating there's more to
Oh,
go.
there is more.
Oh, yes. Okay, so this is chapter 3, number 22. We've got A is a member of a group P. You know that A to the 6th is E. What are the possible orders for A? What's one clear order?
6.
Yeah, lovely, right? So definitely 6 is one of those possibilities because that's literally right here. Using exponent properties, how could I write 6 as some power to another power? What are some combinations I could do? Yeah, so like, you're like this, right? Yeah, yeah. So that's a possibility. What's another one?
A squared to the 3rd.
Square to the 3rd. So, what are some other possibilities for the order of A? If this thing is equal to E, maybe it's A to the 6th that equals E, but maybe what else could possibly be E? Heard some air leave your mouth, Trinity. Kind of a light whisper. What are you thinking? Yeah, that's right. So if A squared is E, then A to the 6th is also E. You see what I'm saying, Sydney?
No.
So look, so if A squared is equal to E, then what is A squared cubed?
6.
It's A to the 6th on one side, but what's inside here? What is A squared?
Oh.
So what's E cubed? So it's also possible that the order of A is what? 2. Yeah. Because it might go to E before the 6th,
Okay.
and then you're just taking a multiple of that. What's another possibility?
Could be 3.
Could be 3 as well. Are there any other possibilities? So let's think. So now we've got that. So this will take, it's a little arguing, some words. What is happening here? What is allowing me? What is allowing me to do this game here?
Well, those are factors of 6.
Factors of 6.
So
yeah.
4 wouldn't work, and 5 wouldn't work.
Solid.
Okay.
Yeah. So the GCD of these things with 6 is, the GCD of the things with 6 that you're mentioning was 1, right? So we don't know anything about that because we can't get a multiple of that to 6.
Okay. That makes more sense.
Yeah, cool. So any divisor of 6 is a possibility. And then just argue that out. Cool. Well, that one's easy. Done now, right?
It's easy now.
It's easy now. So I'm saying, I don't mean like in general. Yeah, saying things are easy or trivial or clear in math is just an asshole move. And it happens way too much. What else?
Can we go over like the concept of those cyclic groups again?
And we're definitely going to do so today. So like, do you have, like, what in particular is bothering you?
Like understanding when something is cyclic and when it's not. Like number 27 kind
Okay.
of dumbfounded.
Yeah, I needed kind of just an anchor here for us. Oh, okay. Oh, okay. Yeah, let's take a look. And this is kind of part of what I wanted to talk about today, so thanks for the segue. Let's take a look at cyclic groups, and then we'll come back to your question. You probably have a few more or not? Or not? Is this kind of your main question?
I think this is my main one.
Anybody else have any specifics on homework you want to talk about? You do, Trinity? Yeah, I do too. Awesome. Oh, awesome. Outstanding. Well, let's talk about this question. Which one is that you just asked about?
27.
27. Cool. So actually, let me just get the question out. And this is a good segue. So they're asking us to do a bunch of things here. The first one is show that U14 is the cyclic subgroup generated by 3, and it's also the cyclic subgroup generated by 5. So what this means is that 3 is a generator, and that's a term I wanted to define today. A generator of U14. And what that means is you can get every element in the group by just taking powers of 3. This means that I can also get every element in there by taking powers of 5. So what I would have to do to show this is look at the powers of 3. So 3 to the 0 is going to be 1, 3 to the first is 3, 3 squared would be 9, and then 3 to the fourth, I start wrapping around, because now I'm at 27, so what is that in U14? 13, right? And let's, you might even help to write this out, so it's going to be 1, 3. Pretty much all the odds in between there, they're all relatively prime to 14, so they're all in there. Oh, right, thank you, Kyle. Yeah, solid. Yeah, exactly. Good. Well done. So I just have to make sure that I can get all the powers, get all these 6 things in there, and I've got 4 of them already. Something tells me I just need to look at these last 2 powers. Does that make sense? Yeah, cool. And then the same thing with 5. Generate the powers of 5, show that they are this subgroup, and show that they generate U14. So, oh, I'm sorry, was there a question? I thought I heard something. I think maybe it was your calculator, your phone moving or something, yeah. So what about 11? Is 11 a generator? So this, we don't know this. What'd you think, Kyle? No? What did 11's cyclic subgroup look like? 11. Yeah, that sounds about right. So we've got 11 to the 0, 11 to the first, 11 squared is 121, which when we divide by 14, what did you say it was, Kyle? 9. So I'm taking Kyle's word for it. You would want to show this. Don't just write that down, but definitely show that using modular stuff. So all the powers of 11, and then 11, so this is 11 to the 0 first squared, and then 11 cubed takes us right back to 1 again. So I can't get out of this group with powers of 11. So it forms a subgroup of U14, but it does not generate the entire group.
Oh, okay.
See? And I kind of think maybe now the rest of that will be a little easier, right? So and we'll have time to work on it today. You can maybe go check it out.
Okay.
That's intuitively what you need to do there.
That makes sense.
Yeah. Yeah. The next one, U20. I don't know how big U20 is. Hopefully not very big. 20.
It's 8.
8 things. Okay. So you got to check some stuff.
One of my questions was, is there a simpler way to do this?
Well, that's a good question. Okay, let's take a look. All right, let's take a look.
Faster way to go.
So, okay, so U20 is going to be 1, 3,
7, 9, 11, 13, 17, 19.
Let's see. Is there a more clever way? Probably not.
I didn't think so.
Unfortunately,
I didn't come up with that.
yeah. So you literally just have to go through. I mean, this you don't ever want to mess with that because that's in this group. It's just going to be itself. Does that make sense? It's just 1 times 1 there. Like it gets stuck. That's not always going to be the case in any group, but for U20 or any of these U groups, that works. And then 3 is going to get me 1, 3. And then 9. Yeah. Why is my brain frying? Because I guess it is 7. Is that it?
Yeah.
Yeah, that sounds about right.
So it's to 81.
Got it. Got it. Yeah. Cool. Yeah, that makes sense. So you're going to have to go through these 8 things and to show that there ain't that.
Okay.
Yes. Got it. Good job.
Good job, Ralph.
Good job.
Except now I have to do all of that.
Oh, well.
He looked at it and said, there's gotta be an easier way. Dr. T said no.
There is no
And I was
easy way.
pissed.
No. Use it as a meditative.
No, I literally said, can I show this simply? And, no, I didn't think I could, but I wasn't gonna.
It was wishful
I was on
thinking.
hour 6 of homework at that point yesterday, and I was like,
How does your brain function for that long?
Intermittent breaks.
I take
2 hours before 11 a.m. kickoff of the NFL, take a break. Halftime, start working again, take a break, start working again.
I do one problem and think that I need 2 hours of TikTok. That's my issue.
2 hours of TikTok
Yeah.
is.
That's why.
Might as well smoke a pack of cigarettes.
That's why I
TikTok
don't
is
have
my
social
issue.
media, because I get stuck and drown in that stuff.
I use too much TikTok too. I'm just
It's
kidding.
my favorite app. It
It's
really is.
pretty awesome. I actually learn awesome things on TikTok. We will have a result, Kyle, in the next chapter. That would make it a little easier. And and that's actually Theorem 4.2 that I asked you to read for Wednesday.
Oh, poor guy.
So if you want to read it and employ it,
I'm gonna do that.
okay, I take it. Yeah, that's great. Let's actually look at it. What the fuck? Why not? Right? Why not? It's in the book. This is a very math booky kind of thing to do, right? Have you do something brutal and then give you the tool to use it. Go dig that hole with your hands.
Oh, it's like the beginning of calculus is you have to use the long way of doing derivatives.
Everything, yes,
Then
by
you do it.
definition.
You get fun rules and then everything's just smooth sailing.
Okay, so theorem 4.2 that we have the cyclic subgroup generated by a to the k is equal to a cyclic subgroup generated by the GCD. And I'm not going to prove this today, but if you read it, then we'll be able to prove it easily on Wednesday. The GCD of n and k. So when we come over here and we're asking ourselves, well, is this, let's see, let's try, hold on, I don't know if this,
Don't get his hopes up like that.
I know, I'm really getting his hopes up. I think I got your hopes up too much. I was hoping it would knock this shit out, but, so here's the problem. So can you see why I might have thought it might work? Yeah, right, like at first glance. But then we actually need to have each of these things as a power of something else. So, for example, we take 3 here, and 3 generates the cyclic subgroup. So I ask myself, what cyclic subgroup does 3 squared generate? And that's going to equal 3 to the GCD of, and let's see, so this group is actually order 4, right? So 2 and 4, it really doesn't, wait, is that right? 4, 2, 3, 4, GCD of 2, and that's just 2, right? So it's 3 squared. So let's actually check this out. Does 9 should generate the same subgroup? A little dicey about that. I'm not dicey. Well, I'm not. 1, 9, and then 81. No, 81 takes its full realm, doesn't it? Oh, it's the n. The order of the group is actually n is. Maybe I'm not employing this well at all. I don't think I'm employing this properly. Because, yeah, I think this is wrong, because in the assumption up here we have that a to the n is e. So actually, the order of a is assumed to be n in this theorem. Maybe it would have been good to wait. Now I see. So if I know that the order of this element is n, then when I raise it to a power, I'm going to have this result. But wait, so the order of 3 is 1, 2, 4, 3. I think I'm going to pull back from this.
That's fine.
Because I don't think I'm thinking properly here. Let me actually read the statement.
For most of yesterday's.
Is it? I'm sorry. So an order, A is an element of order n in a group, and k is a positive integer. Okay. So the order, well, this should work. This should work. It's just in any group, A is an order, element of order n. So 3. The order of 3 is 4. Does that sound right?
Yeah.
Yeah, okay, I was just like, am I not thinking properly? And so the order, oh, yeah, no, no. Look at this, so look at this result with me. The order of a to the k is, I think, so I've written it down properly, but we have the order of a to the k, or the cyclic subgroups are the same that way. But the order of a to the k is n over the GCD of nk. So that actually seems right. But this is concerning me. You know, am I thinking improperly here? So this is totally true, because the order of 3 squared is equal to the order of 3 divided by the GCD of 3 and 2, and that's 2. So we see that that's 2. Oh, no, everything's fine. Okay, this is fine. It's all true. This is just saying the order of the group generated by 3 squared is the same as the group generated by 3 squared. We're all good. Yeah. Needed to warm up there a little bit. But it doesn't do shit for this problem. Way long story short. We could have literally computed all those powers and we'd be done with this already. So that's what we get for trying to learn. Trinity, you had some questions, my friend. And then Kyle, I know you do too. Yeah, that's cool. It gives me some board clearing time. Any of you actually planning on coming to math club tonight? It's okay, you can be honest with me.
If I'm awake.
No, there's some soccer thing I have to do. I don't know
Oh.
what it is.
I have orchestra.
What's you have what it for? No. Shit, I would have brought, I'll bring, then I will do the tricks. If you don't make it, I'll bring the tricks on Wednesday and show them to y'all. Cause the one is just like one of the greatest tricks I've ever learned. So yes, did you find your problem?
I wanna go get 24.
Sure.
I am so eager to figure out 24.
Okay, cool, we better deal with this shit.
Cause it'd be easy if it was available, but it's not.
Correct. Okay, so let me give you some tips on how to proceed here. So we've got group elements A and B. Prove that the order of AB is the order of BA. So is that where, just start there?
Yeah.
Okay. Great. Yeah, and we don't know it's available. So let's assume that the order of AB is N. So with these order things, sometimes it's good to just anchor things right off the bat. Yeah, okay, that's a great move, great first move. So that means that, okay, it's okay, okay, it's okay. And then let's write this out. Yeah?
I did that too.
Okay,
Still,
cool.
Okay.
Okay. But you're doing all the right moves, Kyle, so that's awesome. And there are N of these things. I didn't do that one. Okay. But you knew it. Yeah, you knew it. You remember. What's that?
I also didn't do that.
Okay, cool. Well,
Here we go.
all right, here we go. Any suggestions on the next move? I mean, all those parentheses. Do I have to have parentheses? Make some moving shit around, right? Yeah. So let's just get rid of the parentheses. Okay. So now what we want to show is that N copies of BA get me E as well, right? So what I want to show is that BA, want to show BA to the N equals E, in other words, BA equals E. Boy, these look similar.
Yeah,
So close. How could I perhaps just manipulate any of this, right? Like, I mean, I could start multiplying by things, left multiply by an A inverse, but I could do that. I could also left multiply by a B. Could also do that.
Oh,
Maybe.
Never float your boat, truly.
Yeah. So I'm actually kind of curious here too. I'm not 100% certain what's going to work, but let's try some things. So that means if I left multiply by B, A, B. And let's not write any of this down until we see what's up. And then maybe right multiply by A.
yeah.
Why not? I'm just, what the hell? Okay, there's BA, right? So let's see, we started with, I kind of want to line this up so we know where we started. So we've got this AB. Anytime I have AB with N copies of it, I know I can replace that with E. Okay, so this is, now that just gets us back to BA, right? If I replace this all.
BA equals BA.
Yeah. What about, well, I'm just gonna see what happens here and just try some things. So if I do that, then that's all, this is all, let's see, where do I go? How many copies do I have Well, that doesn't get me anywhere, because I've still got A, B. It's something like this. It's definitely gonna be this game we're playing.
Is it necessary to like write it out, or can you just write like A to the N, B to the N, like distribute that into the?
What is the answer? Anybody have the answer to that question? When can I do?
Can't do it here, basically.
You need a billion, right? Yeah, you've gotta be, yeah, that wish so bad that we could do that.
That would make life so much easier.
That would be way so much easier, and we could just knock this out right away because this would be VA. Yeah. Okay. So let's see. This is fun. I'm gonna go back. Go ahead. Yeah.
I think maybe, so get rid of the A on the left.
On the left thing. Okay.
Because now we have it in like BA, you can group it like that, and then it would be BA to the N plus one,
Oh.
right?
Yeah. You're absolutely right. So let's see. So here there are N. So I did a left multiply by B and a right multiply by A, right? Yeah, so I've got 1, 2. So I've added an extra B.
So it's B, yeah, plus one.
So this is like so. Oh. Yeah. And then what if, since this is a group, I know that BA is also in the group. And I know that there's a BA inverse that exists. So where can I go next? This is cool, yeah, this is the way. This is absolutely. Yeah, exactly. Yeah, so we can just rewrite it like this. Yeah, beautiful.
I swear I was like dancing around here, and I just never actually.
Right, it was right in front of us all. It's just right here. And so then left multiply by VA inverse, and we're good to go. That's fun. Cool little puzzle. And what's the next part? Which problem was this? 24. All right, so then the next question is prove why. Why does this show that the order of BA or ABAB, ABBA, ABAB, is BABA? Then, so, this shows this. Is this true? This is fun. Oh man. Is this true? That the order of ABBA is BAB? Let's work on this together. Yeah, let's think about this. Why is that true? this is, oh, okay, this is the fact that we need to use, not this crazy shit down at the bottom. Okay, that helps, that definitely helps.
About to send you an email this morning.
All right,
Actually,
send
this
it away.
afternoon.
Okay, I'll be looking for it.
All right, there's something to do.
All right, good, okay. None of you were in the class that I had where there were some carolers coming around, and we locked the door and pretended like we weren't there. 'Cause we were all like, this is all like these math folks not wanting to like listen to carolers.
Fair.
Yeah,
Fair.
yeah. Too much social interaction. Trinity, you were gonna say something, it looked like.
Well, my thinking on this, could we like condense like AB to be AB in parentheses squared?
Let's think about it.
Can we do that?
Yeah, that sounds,
Cause
yes.
then if you do that, then the order would be AB, well, it'd be like two N, right? If we assume that like AB is N, then the order of AB is N, like we did over here.
It would be n over two,
N
right?
over
Is that, I think, cause then, explain what you're, yeah, so I'm not quite sure I get the two n part, so let's see, so, I like this, I think that's a cool move. So then.
Cause you're trying to find the order of like AB squared.
Yes, so what, yes, oh, this might be good, so what if, because if n is even, then that would work, I think, right? Like, we could
Yeah.
raise this to the n over two, and then that would get us to a nice, right, I could do this. But, and what if n's odd? And that's what I was thinking here, I was like, in the odd case, and I feel like we could do it without, but let's say that the order of ABAB is, K. And then if I take this and raise it to the K, this is this to the K, and that's E. So I like your idea very much, because then we know that AB to the 2K is E. Right, yeah, so that, yeah, that's where you were thinking of 2N, I guess, right?
Yeah.
Yeah,
was
yeah.
that was what we did.
Got it.
So-
And we know that the order of AB is equal to the order of BA. So it means AB to the N. Yeah, when n is even, it seems pretty straightforward that the order of each of these would be n over two. You just need half as many to get the nth power of AB or BA. So this is what we. Stop trying to be so sophisticated. Look at this. So this is A, and then I've got. Let me get back to N. We just played the same damn game. So yeah, in the case N is even, Trinity, I think, that definitely going down that route. So, yeah, this seems clunky and unpleasant, but let's just grab what we can. The order of AB equals N implies that the order of AB is N over 2. Does that make sense? Because I need half as many of these multiplied together to get the same string of ABs. So that sounds okay, but what if N is odd? So come back to the little game here. So let's say that the order of AB is 3. What is the order of AB? So to get back to parity, I can't just tack on another one. So that gets me, now I've got 4 of the ABs. But if I do it again, AB, then I have a multiple of 3 ABs, or 6 ABs, right? Okay, this is starting to maybe feel a little bit better. So here, then that gets me back to, because then I've got AB, there's one group of them, and then here's the other group of them. Just playing, right? Trying to look for patterns. That feels about right. So here, if N is 3, the order of AB is 3, then the order of AB is also 3? Huh, okay. Right? Am I at least being consistent with what I've got written there?
Yeah.
Wow, so I kind of wonder if N is odd, if the order of AB is the same as the order of AB. Or if it's some kind of like common divisor nuttiness. Let's see, let's try this again. So let's say that the order of AB is, let's pick something, well, when it's even, it's easy. 5, what the hell? Oh, go to something with multiples, there we go, like 15, oh Jesus. Yeah, I know, I don't want to, like, but I'm trying to think of the 2 lowest numbers I could multiply together to get an odd number. 3 squared. All right, let's just do 9. See, that worries me for other reasons. It's it feels like it won't be as informative. Now, fuck it, we're going to 15. We're going to 15, which is 3 times 5. So, what is the order of A, B, A, B? And we don't have to write out, we don't have to write out 15 of them, but we know that this is going to be E, and there's 15 of those E's. So if I start writing up these, and I copy down 15 of them, and I've got only 30 elements here, so that's not too bad. Well, that definitely would be E, right? At that point, because it's basically 2 copies of that, of that. I guess the question is the order, could the order be smaller? So inside of here, so how many things are there? There are 30 things in there, and then there's just 2. Well, we'll hit it way too. Yeah, that'll work. There's 30 in there. 30 separate AB, yeah, 30 elements and, or ABs, yes. I guess 60 elements.
60, okay.
Yeah, 60 elements, so 30, sorry, not writing ABs in there. And so 15 of them will go to E, then the next 15 will go to E. And we have to have 15 to get to E. So that sounds all right. So, okay, what about this? Just a proposal, claim. If the order of AB equals n, then n even implies the order of AB is n over 2. Because that gives me, if like half as many of these gives me what it takes to get, right? Yeah. And then if n is odd, the order of AB is n. But could it be less? So, like, could I get away with oh, I just doubled it. Yeah, I just took in copies of this, so. But could I get away with less? Could I get away, like if I took 3 copies of that? What would that give me? So let's see if I took AB, right now there's 15 copies, and then I did that 3 times. Just thinking of divisors. So that's gonna give me,
You have 45 ABs, which doesn't make a full AB.
yes, that's correct. Yeah. So this is seeming right. So this does seem right. I haven't really proved it. And so there's not really much of a proof. Feels like it should be easier than what we're doing. Okay, I'm gonna start again. Start first principles again. So if the order of AB is n, then that means this. And there are n copies. Right there. Oh, okay, I think maybe. So, there are n copies of this. So, what is the order of AB? AB. Well, if n is even, and I'll just cut these into groups of 4, and the order of AB is gonna be n/2. Like, to me, that, I don't know, that seems pretty obvious, but maybe not. Does that seem, yeah, like, that seems pretty obvious to me if n is even. So then let's say it's not, and I've got this. So let's start trying to make copies in here. So I'm gonna run into a problem when I start trying to group by twos, because I only have an odd number of copies of AB. So by the time I get down here, this one's not gonna have a partner. And so what does it take, what do I have to tack on there to get it a full partner? Well, I can't just tack on AB, because then that's gonna leave me with this fresh AB. Right, because this is all gonna go to E, right? This stuff's all gonna go to E right now, because there's n copies of it. But when I start grouping by fours, and I wanna make a perfect group of four, I tack that on, this is just gonna be AB. So AB, AB, so n is odd. To the nth. So right now, that's equal to AB. And then, so I start tacking on more ABs, AB, ABs. Right now I've got an even number of ABs, so I'm good to go. I'm gonna keep tacking on then AB, ABs. And I'm going to have to keep going up to n more copies. It seems so just convoluted what I'm doing here. I don't think it's this complicated, but maybe. Do we have any nice results that I'm just forgetting about? Like, just
I went through, like, chapter 3.
didn't see
We
any,
talked about orders, and we said,
nothing good in there? No.
what's I missing?
Well, I don't know, you're a pretty good reader. Yeah, there's not much at all, is there?
It just talks about order, and then it talks about, like, separate
Yeah, yeah.
situations.
There's gotta be something simpler than what we're looking, which one was this? I'm sorry, what number? 24, thank you. Okay, well, maybe for insight, let's look at the last question. The order of ABA and the order of BAB. That might give us something helpful. So we're gonna assume that, and then what about the order of ABA versus the order of BAB? So what do we gotta do to get, and we're gonna assume that this order, let's pick an order, like a solid one. Let's go with odd, just for the hell of it. See, maybe something weird will happen here. So let's say the order of AB and the order of BA is 3. So what do we got? AB, AB. So we got that. Then let's see, could the order of this be 3? So we've got app. No. Oh. So not having that, not having the pairing makes this choke, because we can't get that rhythm. So I don't think we can say anything about that, but maybe, I don't know. So what is this then to the third? It's bab, bab, bab. Yeah, that looks terrible. mean, I don't know what we do with B squareds and the A squareds, how we can possibly reconcile that. Okay, I think, like if I was writing this up and it were due tomorrow or something, it's not, right? But if it was, I would go with my even and odd argument because I feel like that at least gets us some purchase, and I think it's true. That if the order n is even, then the order of AB is even, then the order of ab is n over 2. And but that's actually still not even the problem, right? Okay, wait. I think maybe that was a better way to approach. So let's say that the order of ab is k, then that means ab k times. Maybe I've already been down this. Maybe I've already been here. I've got k of those. Yeah, and I think this is what ended up leading me to that other argument. So at this point now, if k is even, I've got 2 copies. Wait. So this is probably true. Okay, so K. Damn, man. It's just not seeming like there's anything clean to do. I'm not feeling like there's anything clean to do. But maybe the problem is I'm still like choking on trying to do this with these K's and stuff. So let's say this, and okay, so I've got K copies of this. And so that's this statement. But what I want to show is that this is true. So is there any, what do we have to do to get K copies of Baba into this?
Multiplied by B.
Left multiplied by B?
Right, multiplied by A to get another A at the end and that all. Then you'll have K copies of the ABA, and then 1 copy of BA. And then equals BA.
And then we still got the BA though, right? Yeah. But that's okay, this is actually feeling a little bit.
Yeah, and we showed earlier that BA has inverses over the group, and we can do the same thing we did earlier, can't we?
Yeah, I think, yes, that's it. Yes. Okay, it was so much, yes, that's it. That's totally, so, let's start, yep. I was trying to get too fancy and counting and all that stuff was just starting to hurt like hell. So, let's look at the argument again. That's it. So here I've got K, if the order of this is K, this equals E. right? So I'm writing that out. Then we're gonna left multiply by B. I'm gonna right mult by A. And then what we're gonna get is B, and let's keep all the parentheses and stuff in here. Oh, yeah, it's like, it's the same shit.
Yeah.
Jeez, oh, it's okay. It's good to suffer together. Does everybody see what actually the issue is here? So now that I've done that, I've got a BA, because I tacked on two things. I'm gonna pull two different things out from the left. And then I'm left with K copies of Baba. And my share is sinking, that's weird. Yes, that's it. That is it. And then there's K copies of this. And then left multiply by BA inverse. Shit. That was hard one. Wowza. Cool. And then on this one here, it's not at all the same kind of thing.
Yeah.
Right? It also seems to depend on just way too many other things. So in this one, I would just address what happens when you multiply these things out, and how the A's join and the B's, they butt up against each other. You lose the rhythm. Whew. What other problem did we want to talk about today? That was exciting. It's so simple in the end.
I think I was overthinking 34, but I just didn't really know where to go.
Okay, let's take a look. Well, yeah, speaking of overthinking, right? Like literally just overthought a problem for 15, 20 minutes. Oh, that's so elegant in the end. Oh my God, once you start going into cases, like it always feels like a bad place to go.
The cases are not fun.
They are not fun, and often it's like a sign that you're not thinking elegantly enough. You're not thinking at a high enough level. So number 34, H is a proper subgroup of Z. Under addition, kind of implied, and H is a subgroup of, H consists of, so let's just add these elements, use the proper name, 12, 30, and 54 are elements of H. Cool. What are the possibilities for H? So,
Oh, you're looking at the.
am I looking at the wrong problem,
Yeah.
Kyle? Which problem were we
Well, I
looking at?
guess it's
It's the same concept.
the
isn't it?
same concept, just different numbers. 34
Oh.
contains 18, 30, and 40.
Cool, well, let's do this one. It's all the fun's left. Yeah. Same problem, different numbers, good. This is 33-ish, perfect. So I've got a group with addition, and it's a subset of the integers. What can I do with these elements if H is a subgroup? It's like, let's start constructing things. What was that say?
Subtract myself, sorry.
That's okay. So like, give me one other thing that's in H. What is H closed under something? It's closed under addition. So any sums have to be in there, right? Yeah, so all sums. So let's actually start making a little list out here. So we've got 12, we've got really a little space, I got 30, I got 54, and then I've got 42 in there because I add these two together. And basically what I'm gonna have in here, I can have any multiple of one of these. So I can have k times 12, that's an integer multiple, plus any integer multiple of 30, plus any integer multiple of 54. right? So if I start, those are in some ways generators of this subgroup. So we're looking at the subgroup generated by 12, 30, 54, using that notation we did last time. Not cyclic necessarily, it's just, well, I guess, yeah, it's multi-cyclic or something like that. So gosh, I think at this point, you know, it's like just start playing around until you see the resolution you can get. Remember, we did something like this where we had a subgroup that was generated by two things. This was one of the examples, like we had 5 and 7, right? And like, what was the subgroup generated by those? And it turned out to be the GCD of these two numbers. Do you remember that at all? Pretty sure we did. I vividly remember it, yeah. So, for example, we had the subgroup of Z generated by 8 and 14. Remember that? Yeah. Got it written down here. And so that's basically the collection of all multiples of 8 plus all multiples of 14. Yeah. And we realized that we could actually get this down to this is that GCD linear equation. So there's a K and an L that gets this down to all multiples of the greatest common divisor of those two things, which is just 2. So it's actually, everything in here can just be a multiple of 2. So what we want to do is figure out what is the smallest multiple we can get. And maybe, what if we broke this into multiple steps? So for example, let's forget about the m plus 54 for a second. So we've got this 54 still, but we could have a 0 in front of this. We could have none of these, and we're just working with these first two. So what about the subgroup generated by 12 and 30? Using that logic of last time, what is this the same as with a single generator? What's the GCD of 12 and 30? 6. So anything that I can make with linear combinations of these two, I can get by just as a multiple of 6. Does that make sense, or does that need explanation? Because I'm happy to talk about that. So these two things generate just multiples of 6 at their finest level. That's the best you can do. Think about it, right? Like 3 times 12 is 36. I subtract over 30, I get 6. The finest resolution of these two is a multiple of 6. So then what if I take that subgroup and let's say what about this? What is this going to generate? What is the GCD of 6 and 54? Yeah, I think. Oh wait, no. Oh yeah, 6 times.
Yeah.
6. Yeah. We forget sometimes the basics dissipate. So this argument tells me that probably the finest resolution I can get out of this set is down to 6, no matter what combinations I take. And actually, I feel really confident about that. Does it make sense what I did? Do you want me to talk it through? Trinity, you feel good about it? Friends down on this end, the west side of the table. Do you want me to go through it again? Are you good?
I think we'll be okay.
You think you'll be okay? Awesome. So yeah, it all comes down to that GCD thing. And just to make sure, what if I did it a different way? What if I pulled out the 12? And I just want to do this for myself. So like 30 and 54, what is the single subgroup needed to generate that? Looks like a 6 again. And then when I go, okay, what about 6 and 12? It seems pretty clear that 6 is going to be. So this is feeling like a really solid approach. Anything else in that homework set? I think hopefully we've kind of addressed all of them, have we? Is there any we haven't talked about?
Just the last one, I think.
What is the last one?
Or 66.
66, let's take a look. Oh, that just sounds like,
Guess and check.
get cracking, yeah, that's like,
Oh, line.
And it's all under mod 40, right? Every operation that we're using.
yes,
Okay.
exactly, mod 40, so a non-cyclic subgroup.
Sick.
That one's not fun.
Yeah, what's in U40, I'm curious, let's take a look, let's write out U40.
1, 3, 7, 9, 11, 13, 17.
Whoa.
Slow down,
Whoa, whoa, whoa.
slow down, buddy.
Kyle!
1.
3, 7,
I'm just
9,
kidding.
11, 13, 17, 19, 21, 23, 27, 29, 31, 33, 37, 39.
Good God.
How about no?
Yeah, so originally,
So what would it mean to, what do we mean when we say non-cyclic subgroup?
so
Let's make sure we understand what we gotta find.
the order of one of those elements doesn't have the same order as any of the elements in that. I don't know how to explain it.
That
But
there's
I
no,
don't think
there's
I'm
no
not-
one element that generates the whole subgroup.
Oh, so you really do have to go through all of them?
Maybe, I mean, we could, let's see if we can maybe think about this.
Start on the low end.
Let's just, you know, I'll look online and see if I can find some tools for us that might help. There might be some not like Chegg.
gotta pay for
That's
that.
not a tool, that's a crime.
It's a crime you gotta pay for, so it's irrelevant.
Yeah, exactly, yeah. So gosh, so 3 squared. Okay, so yeah, let's just kind of, and it might come down to just taking a couple cyclic subgroups and putting them together and seeing, just the smallest ones I can get, kind of putting them together and seeing how their elements interact and do they stay in the set or go out, and then just adding things in a little bit at a time, if that even makes sense. So let's see, so 3 cubed, it's 27, 3 to the 4th, that's 81, and that gets me back to 1. Right, so 3 looks like, yeah, 1, 3, 9, 27. Yeah. So then let's take a look at another one. Have you already cranked out some of these, Kyle?
Yeah, 27 has the same order.
27 has the same order as 3?
Yeah.
Is it the same subgroup?
Yeah.
2, that makes,
Yeah.
okay, that makes sense. Let's just take a look at 7, what the hell, so.
Is
7.
that
Oh,
like a
so here we go.
Is that a coincidence that they're the same?
I don't think so.
Because, so then you would know that like 1 and 27 wouldn't be, like just based on 3, you would know that those 4 would not be what you want.
Say that again.
So like you're trying to find one of those numbers that produces like the whole group, right?
I wanna make sure that it doesn't.
Or that it doesn't, right?
Yes, yeah.
Okay, so then you've already figured out that like those ones haven't?
Does, yeah, so
So
they
then-
definitely don't generate U40, absolutely.
So
And we're
you
trying to
don't
find
have
one
to
with an
check
order of
those.
4 too. Like that's the thing, is we're
Oh,
finding.
did it say
Yeah,
that?
Yeah, so
Oh,
it has to be a subgroup of order 4 that is non-cyclic, which is what adds another even part to this. 7 does work though. 7 is order 4, so. 7, 9, 23, 1.
And then what was the?
7, 9.
Oh,
23,
7.
1.
Really? Wow.
Pretty sure, unless I mean,
Oh, that looks
granted, like I
weird.
said, this was hour 5.5.
Yeah,
hours,
that's,
so-
that sounds a little surprising. Let's just check that out. So, yeah, you're right, cause 7 times 7 is 49. Yep, and that's 9.
343, which 40 you get to 320, so yeah, 23 times 7. 240 by 6. Yeah, that's right.
Okay, so it's interesting they share an element. So what would happen if I started just kind of putting these together? So let's see here, so we got 1, let's say we put in 1, 9, So that's a little subgroup on its own, so that's just 9. This is a subgroup of order 2. Is there another subgroup of order 2 in that? This little collection here?
No.
No, doesn't look like it. What's 23 times 23? I don't.
469.
469, that's 529. 529 divided by 40 is 9. So 23 squared is 9. That sounds.
Yeah, cause 40.
So what if I put 23 in here? Then what's 9 times 23?
I guess I have a calculator.
Yeah, you're the count. Yeah, you're like the guy with the truck who helps everybody move.
207.
207, which is 7. So what if we put a 7? So 7, 9, 20. Okay, we're just back to that shit.
Sorry, that's 7.
Yeah.
Yeah, this is when I said, I don't feel like working this all out, give up. For yesterday, I gave up.
Well, I'll work on this one too and send out hints if I find any. But I think at this point, it's just gonna be a game of playing.
I'm hoping 7 works, but I don't think it does.
I think there's a bunch of subgroups of order 2, right? So we've got 11, I think, is a subgroup of order 2. So 1, 11, 11 squared is 121, that gets me back to 1.
Yeah, 7 doesn't work.
When 7 doesn't work, what do you mean by that?
Cause like, then aren't we having to take each of the elements within that subgroup that is 7 and then test those to see that they don't have the same order as 7? Or am I doing the wrong thing?
We just, the key thing would be, we don't want them to be powers of 7. So like, I just wanna make sure that like, in this case, everything in here is a power of 7. So this doesn't work. We want something where there's no one element whose powers generate everything in the group. And it has to be ordered 4. Does that not?
I don't think.
Okay, then let's keep talking. So,
Gotta go to
okay, so let's say, however many elements are in here, I don't know, I know we gotta go. I'll think about this and send out some tips, but let's say there's like 11 things in here. So if the problem was 16, find a subgroup of order, a subgroup of something that's order 16 that is not cyclic. This would work because, well, wait, is there one thing in there that generates everything? Maybe not.
13.
But there might be something.
I don't know.
Shit. All right.
13 does not.
That's okay. Okay, I'm gonna work on this one too.
I don't know.
And I'll send out any tips I have. I think it's just gonna be a matter of exploration.
Oh,
Yay, yeah, there you go.
Guess and check.
That's the attitude.
Do you have office hours today?
I do. Like right now, like after class. Why, what's up? What's,
doesn't matter, help.
you need help?
Yeah.
Oh, okay, we could.
I'm done at 11:50.
Well, why don't you come by my office then? Cause I'll be there till 12:20.
Okay.
We'll have a little time together, does that sound okay?
Yeah.
Okay, awesome.
I just popped my
And
nose
then,
so hard.
actually, Sydney, I'll be in there before math club.
This is literally my last class today, so my next one.
Okay, okay, cool. And yeah, come by, and if we can't get it figured out by then we'll